Before we begin, the meeting is being recorded and will be posted on YouTube afterwards. Everyone who speaks during today's event will be part of the recording. We will do the Q&A at the end of the presentation. If you choose to ask a question, your voice and image, if you have your camera on when speaking, will be part of the recording. If you do not ask, you will not be part of the recording. If you are using the most recent version of the app, which we recommend, you can use the raise hand function to join the queue. If you're using an older version of the app, which does not have this function, please use the chat to let the organizers know you would like to ask a question, and they will add you to the queue. The organizer will let you know that when you are next in the queue, so you can be ready to unmute your microphone and ask your question. If you do not want to be part of the recording, the organizers can convey your question to the speaker. In that case, please type your question in full and let the organizers know that you would like them to present it to the speaker. If you have any technical issues, please message the organizers for assistance. If you drop out of the meeting and are unable to rejoin, you can post a message on the event page, on the event meetup page, which we're monitoring during the presentation. Disclaimer, SFPUG, Bay Area Postgres, is a PGUS affiliated user group, and I am a volunteer for PGUS. SFPUG is sponsored by PGX, and I work for PGX. And without further ado, here is Rajan Palanivel with leveraging a PL REST extension to protect sensitive data in PostgreSQL.
All right. Thanks, Catherine.
You're welcome.
All right. So, hi, my name is Rajan Palanivel. I'm from the engineering team at Baffle. So, Baffle is located in the Bay Area, Santa Clara. So, the topic for today is transparent application layer encryption for Postgres using Postgres extensions with PGTLE and PL REST. I'll go over the details in the following slides. So, the agenda for today is a short introduction about Baffle and what we do, followed by the current state of data encryption in Postgres. Then I'll go over the application layer encryption, the need for application layer encryption, and the threat model. And I'll go over the next item will be the challenges with implementing application layer encryption. Then I'll go over how we can actually solve the challenges, application layer encryption challenges with Baffle architecture. And after the architecture discussion, I'll go over some of the customer use cases for this particular encryption model. And I'll go over the some additional details about our our product design, as well as the PostgreSQL extensions, a bit of a high-level design overview. And I'll go over some additional information about how the extensions were implemented, different ways of implementing extensions, and compare and contrast the plus and minus of those extension implementation options. Then I'll summarize my talk. And so please feel free to ask any questions if you have any, so that will be more interactive. All right, so starting with introduction. So Baffle basically is a cybersecurity company that delivers enterprise class data security products. So our focus is the following. So we focus on end-to-end data protection. So we call it transparent application layer encryption. So it includes not just encryption, but tokenization, masking, access control for databases such as PostgreSQL, MySQL, and also for data lakes such as AWS S3, Azure Blob Storage, IBM COS, etc., and data warehouses such as Redshift, Snowflake, and so on. So our focus is on no-code change application layer encryption for SQL applications. I'll go over some of the details later. So that is the first major focus of our company. The second one is sensitive data protection for GenAI application. So GenAI is all about data. So we actually have products for sensitive data protection for GenAI as well. And the last one is application to application encryption is primarily on REST API based REST API protection. But today's talk, I'll focus only on item number one, this transparent application layer encryption for Postgres databases. Okay. So this is the current state of data encryption in Postgres. We all know about transparent data encryption. This actually has been around for quite a number of years, almost 2 decades. And we know that TDE actually protects data at rest. So it makes sure that the data gets encrypted at the file system level or disk level. But there are a lot of limitations with TDE. This was designed in a time period where they were like people were worried about storage and medium theft. But transparent data encryption does not protect against the current threats that we actually have. It's typically remote users, compromised credentials, and also those kind of threats that are not protected by transparent data encryption. And another thing is that TDE is not available in standard Postgres versions. It's actually an add-on. So the TDE has been around. It served its purpose, but it is not the current. It's not going to protect the current threats that we are facing against. So the solution is application layer encryption. So here the data gets encrypted and remains encrypted end to end. It gets encrypted at the application level, and then the data ends up encrypted in the database level, and then remains encrypted all through the database operations on the data and so on and so forth. So this kind of end-to-end data protection to make sure that the complete pipeline is protected. So this is the one that is needed for protecting against the current threats. So I'll go over the threat model and what application layer encryption protects versus what transparent data encryption protects. That will give a good idea of why ALE is needed. So if you see the slide, sorry about the font size, but the main problem with transparent data encryption is, as I mentioned before, it protects against disk or storage medium theft. But it does not protect against data from, for example, database administrators compromised DBA credentials, for example. And it becomes worse if the database is administered by a third party, like a cloud database or hosted databases. So the data is not under the enterprise control when it is moving to the cloud database, and there is a need to make sure that the data is protected from the DBAs that doesn't belong to the enterprise. The second one is the compromised database users' credentials. That is also not protected by transparent data encryption, but protected by the application layer encryption. And the application user credentials as well. I mean, the same compromised user credential or application vulnerabilities, or database program vulnerabilities, or data exfiltration. So all those things are the current mode of data hacking, data exfiltration. So all those things are not protected by the transparent data encryption. But application layer encryption makes sure that all these threat vectors are covered. And in addition to that, it also obviously as data remains encrypted in the database layer, it naturally covers the disk and storage medium theft as well. So application layer encryption is kind of a superset of transparent data encryption. The only gap with application layer encryption is where the cloud OS, root OS access to the machine, the physical access to the machine and dumping memory and so on and so forth. That's basically where the application layer encryption will not protect. But at the same time, application layer encryption can work in conjunction with confidential compute or trusted execution environment to cover that gap as well. So the summary of the slide is basically why there is a need for application layer encryption for covering the modern current threat vectors, and why TDE is kind of outdated. Okay. So now we have established the need for application layer encryption for the current threat vectors, but we need to actually go over the challenges. I mean, why is that application layer encryption is not adopted widely, right? The main reasons for that is the traditional application layer encryption, which is also called as client-side encryption. Both are same. They actually need for implementing application layer encryption, the application code has to change. So typically, the way it is implemented is using some crypto SDK or APIs. So that means that the application code has to actually utilize those SDK APIs or REST APIs to encrypt and decrypt the data. So that's basically the first challenge for adopting the application layer encryption. There is a need for application code changes, which is typically not possible if enterprises using third-party applications, legacy applications, or off-the-shelf applications. So that's a major challenge. The second challenge is, so once you encrypt the data in the application layer, the data actually ends up encrypted in the database layer. Now, all the database operations, will basically start to fail because the semantics of the encrypted data is totally different from the clear text data before. So database operations such as sorting or filtered queries or wildcard searches those things will actually start to break because the data is encrypted. And the last major challenges for application layer encryption is basically the burden of actually encryption key management now falls with application developers. So they need to make sure that as part of enabling application layer encryption, changing the applications, they need to make sure that how the encryption keys are created, managed, rotated, and so on and so forth. So basically, there are a lot of uplift that needs to be done for enabling application layer encryption. So instead of the application developers focusing on implementing business logic, they need to spend a lot of time doing these things. But of course, but at the same time, application layer encryption is definitely needed for protecting against the current threats. And how do we solve this problem, right? How do we solve these challenges? So Baffle addresses the above challenges, the traditional application layer encryption or client-side encryption challenges, with something called transparent application layer encryption. So this model actually involves three different, basically the first thing is that how do we solve the code change requirement in the application, right? So we use SQL proxy that sits in between the application and the database, and then that proxy makes sure that all the data is encrypted. So there is no need for changing the application. The only change that is needed for the application is actually to talk to the proxy. The connection string has to point to the proxy instead of pointing to the database. So that's the first way that we actually solve the first challenge. And the second one is, how do we make sure that all the database operations will continue to work even though the data is encrypted, right? So that is taken care by Postgres database extensions, which I'll talk about more in the upcoming slides. So that actually makes sure that all the database operations, even though the columns are all encrypted, all the database operations will continue to work. The sorting and the group by and all the stuff will continue to work, even though the data is encrypted in the database layer. So none of the database operations will break, so that the application doesn't have to do those operations in the application layer, but still make use of the rich database operations as it used to make use of it before encryption. Last one is Baffle also makes sure that the encryption keys are managed without the need for application developers to worry about key management, which is kind of a big task. So yeah, so this summary is basically there are a lot of challenges with application layer encryption, and our architecture makes sure that those challenges are met, and making the application layer encryption easy for adoption by the enterprises. Okay, so now I'll go over the architecture of for Postgres, right? So how we built this solution for application layer encryption. So the first one is, as I mentioned before, there is a proxy. We call it Baffle Shield proxy that sits in between the application layer and the database. So all the traffic from the application goes to the proxy, and the proxy does the necessary transformation before sending the data back to the database. So the proxy is responsible for doing the encryption, tokenization, while the data is on the onward path. And at the same time, when the result set comes back from the database, the proxy is responsible for decrypting the data in the result set, and also making sure if there is any access control that needs to be applied, like masking, and depending upon who is connected through that from the application. So all those things are done by the proxy before forwarding the result set back to the application. So that is the first major component in this architecture. The second component is, as I mentioned before, the Baffle extensions that actually are installed and run as part of the Postgres database itself. So the extensions, in conjunction with the proxy, make sure that all the database operations are possible, even though the data is encrypted in the database layer. And the third one is the Baffle Manager. The Baffle Manager is basically the management console that sits on the side. It's not on the control. It's not on the data plane. Only the proxy is on the data plane. The Baffle Manager is on the control plane and management plane, which actually is used for configuring the proxy. The proxy has to be told which column, which database, which table, which column to be encrypted with what key, and so on and so forth. So all those policies are generated by the Baffle Manager and then pushed to the proxy. The Baffle Manager is also responsible for key management. It means make sure that the keys are created, rotated, and all those stuff. So those things are taken care by the Baffle Manager. So these are the three different components that actually that make sure that we can implement application layer encryption in a transparent way, with no need for changes to the application. As you see the architecture here, the application doesn't change at all. The only change the application has to make is to make sure that the connection string actually points to the proxy instead of pointing to the database. Okay. So now I'll go over, this is basically the architecture. Now I'll go over the several use cases for this particular model and how we are enabling customers to adopt Postgres with these extensions for actually covering those use cases. The first major use case that we have is the multi-tenant data protection for SaaS providers. So one of the things that SaaS providers do is they have data belonging to multiple of their tenants. And this data is commingled in the SaaS platform in the database layer. For example, in the Postgres database, if Postgres database is a backend database for the SaaS platform, then it can be the data belonging to multiple of the SaaS providers' customers are commingled. So it can be commingled in multiple ways. It can be either row level, so the same table can have data belonging to multiple of the SaaS providers' tenants, or it can be database level. There can be multiple logical databases within the physical database, and each database is assigned to one tenant. So that's two different ways, or it can be schema level as well. So there are different ways of actually multi-tenant architecture is implemented by the SaaS providers for their tenants' data. But there is a need for SaaS providers to cryptographically isolate tenants' data within their environment. So there are two reasons for this. One is to make sure that the data is isolated, even though there is commingling of data. This is done cryptographically. And second is basically the SaaS providers will make sure that they won't actually provide the control of tenants' data in their environment back to the tenant. The tenants can actually control the data in the sense that the tenant can disable the key in which their data with which their data is encrypted in the SaaS platform, so that the tenant can disable the key whenever they want to, and then the data in the SaaS platform becomes unusable by the SaaS provider. So even though the tenants have to share their data with the SaaS provider, this architecture makes sure that the tenants have complete control over the data, so they don't have to worry about their sensitive data being they can share the sensitive data to the SaaS providers without worrying about losing control of the data. So this architecture actually provides an option for the SaaS providers to enable either bring your own key or hold your own key model for their tenants. The difference is in the case of bring your own key, that's what this picture denotes. The keys belonging to the tenants are managed by the SaaS provider themselves. So whenever SaaS provider signs up a new tenant, they'll create a new tenant key for the tenant, and then actually manage the tenant's key in the SaaS provider's key management services, and then uses the key for the tenant's data when it is stored in the Postgres database. That is the bring your own key model. The second model is, or the other option is, within the bring your own key model, the tenant themselves can provide their key to the SaaS platform through some portal, and then the SaaS platform can actually use the tenant's own key to encrypt their data. The second option is in the case where tenants doesn't want to share their key with the SaaS platform. They want to manage their own key in their own environment, in their own KMS. This is something called hold your own key. So in this case, the SaaS platform actually using the Baffle shield proxy, the proxy can procure the keys either from the SaaS platform's key store or from the tenant's own key store to do the encryption and decryption. So it can support both bring your own key and hold your own key model. So all this configuration of which tenant key needs to be used for encrypting which row within the table in the Postgres database, or which logical database has to be mapped with which tenant key, are all actually configured via Baffle Manager, the management console. The management console is also built with backend REST APIs, which is typically integrated with the SaaS platform, so that the SaaS platform can enable, or SaaS platform can expose knobs for the tenants to enable, disable, rotate keys in the case of bring your own key. So this actually whole architecture makes sure that the multi-tenant data within the SaaS provider's environment is cryptographically isolated, and then the control of tenant's data is completely given to their tenant by the SaaS providers. It's kind of an upsell for the SaaS providers to make sure that they can implement bring your own key and hold your own key for their tenants. So this also meets the data shredding compliance requirements. So this is basically where the data owners, the tenants in this case, can make sure that whenever they want to, they can actually disable the key thereby making the data unusable, which means the data is shredded, so that the data is actually becomes unusable by the SaaS platform. So this is actually the architecture for multi-tenant data protection for Postgres database. When Postgres database is used by the SaaS platform as a backend database with commingled data belonging to multiple data owners. So this is actually, this slide is specific to Postgres, but the proxy also can, if when the SaaS platform stores data in multiple storages such as Postgres, as well as a data lake like an S3 bucket or AWS, that is also supported. I mean, the same key can be used by the SaaS. The same tenant's key can be used irrespective of where the tenant's data is stored, Postgres database or in some other storages. So this is the first major use case that actually is actually being enabled by us using for the Postgres database using Postgres extensions and our proxy model. So the transparent application layer encryption use case number one. The second use case that we have for transparent application layer encryption is the data pipeline, data analytics, data protection, and data analytics pipeline. So typical data analytics pipeline consists of data ingestion path, where data from various data sources are actually are extracted by ETL tools, multiple ETL tools, and then the data is actually normalized, pushed to the backend data storage. In this case, the data Postgres database. Either Postgres database in the clustered mode or a single instance mode. So this is the left-hand side. Left-hand side is a data ingestion path where data actually gets ingested, and the right-hand side is where the data is consumed by analytics professionals for business intelligence and stuff like that. So this is a typical data pipeline, data coming from various data sources being actually consolidated and stored in a database, Postgres database, and then being consumed by the data analyst, and then the data engineers. So now here our model actually fits in very nicely for providing end-to-end data protection. So in the data ingestion path, the proxy sits in between the ETL layer, which can be any third-party ETL application, Talent, HVR, DMS, whatever, doesn't matter. So proxy transparently encrypts the data that is actually coming from the ETL layer, and then make sure that the data remains encrypted in the database layer. And then on the right-hand side, the analytics application can be any off-the-shelf third-party applications like Tableau or Power BI, doesn't matter. But still, all those applications will continue to work through the proxy, even though the underlying database is completely, Postgres database has completely encrypted data. Another advantage of this model is because both the ingestion path and the consumption path use the same architecture. The same keys and the key management is kind of common. It's common for both. Whichever key is actually used by the ingestion path, the same key is used by the consumption path, so that a single solution actually addresses both data protection for both ingestion path as well as consumption path. So this actually makes sure that the centralized data protection policy for the entire data pipeline with one single solution. So instead of having multiple solutions, it's one single solution. And then it also makes sure that existing applications work even though the data is completely encrypted in the database tier. Similarly, the Baffle manager control plane is actually used for managing and controlling, creating policies for the entire data pipeline. So this is the second major use case for transparent application layer encryption using our architecture for Postgres databases. The third actually use case is also deployed in the enterprise, typically in the on-prem environment, in some cloud environment as well. Big enterprises have a lot of Postgres databases, right? So they have different databases for different of their applications within the enterprise. But they want to actually have a common or a uniform or centralized data protection, architecture to make sure that there is good visibility and the policy enabling policy management, etc. So architecture is something like this. So there will be an application database pair within the enterprise, but each application database pair will have a proxy in between. Of course, with the Baffle extensions in the database layer. So there can be n number of applications, so the deployment looks something similar, but there is one common or single Baffle manager control plane to make sure that the policies are generated and the keys are managed centrally in a central location. and then the whole model is actually deployed seamlessly, and without individual application teams have to actually worry about data protection, management, key management, and so on and so forth. And also it actually ensures the security team within the enterprises to have complete visibility into the security model of the entire all the applications in their enterprise. So this is actually another major use case that we actually have are deploying with our customers in the Postgres environments. And obviously, the Postgres actually enables us to actually build this kind of environment because of its rich extension model, which I will talk about a little bit later. So this is the third major use case. And moving on to the next slide. So I want to actually give a brief introduction about the high-level architecture, high-level design of the entire architecture. So starting with the proxy. The proxy is, as I mentioned before, it is a network layer reverse proxy. It actually understands the client-server protocol of JDBC, Postgres JDBC, ODBC driver, and the Postgres database. So it sits in between the application layer, the JDBC, ODBC driver, and the Postgres database. So it's a network proxy, so it can run in its own instance. Typically, it's deployed in a cluster in the Kubernetes environment, or other types of cluster environment. The proxy consists of a network layer, which actually gets all the packets and then decodes the packet, and then after decoding the ingestion path, so there is a SQL query parser. The query within the proxy, there is a query parser, which actually after the message is decoded, the query is actually extracted, and the query is parsed by the SQL query parser. So once the query is parsed and then the DOM tree is created, then the appropriate transformation is done by the proxy. If the data within the query needs to be encrypted or tokenized, that is done by the proxy. And then once the query is transformed with encrypted data, then the query parser within the DOM tree, the query parser again puts it back into the SQL query, and then the next step is to encode the query within the message, the client server message that the JDBC, the client server protocol supports. Then it is sent through the Postgres database. So as you see here, the proxy actually is capable of parsing the query and transforming the query, and then sending the transformed query to the database. So as the Postgres database gets the query, the data in the query is already encrypted or transformed. So the Postgres database layer never sees the clear data. Now the second, on the reverse path, where basically this is where the data is basically the result set is, for a particular query, for example, a select query, the Postgres database returns a result set, right? So the similar thing happens in reverse. The message is decoded, the message containing the result set is decoded, and the proxy actually processes the result set. Then actually it decrypts the encrypted data within the result set. As we've seen before, the Postgres database only has encrypted data. So the result set that is returned by the Postgres database will also contain encrypted data. Now the proxy actually decrypts the result set because proxy is the one that has the key. Then what it does is it basically does RBAC, role-based access control, based upon who is connecting from the application layer. The proxy can mask the data. It can mask, it can do fine-grained masking as well, last 4 digits, first 4 digits, whatever, depending upon the policy. Then the result set containing the masked values is again encoded back into the message and sent back to the application. So this basically is the very high-level overflow of how the proxy actually does this transparent application layer encryption. The proxy actually, the core crypto is actually built as a library within the proxy. As I mentioned in my first slide, we basically have different flavors of proxy for Postgres, MySQL, etc. The same crypto library is actually used across all the proxies, so that the encryption format, the encryption type is all uniform. So the type of encryption that is done by the proxy layer is all NIST standard AES encryption. So it's actually the standardized encryption. It's not any proprietary encryption. It actually uses a standard encryption, and it's quantum safe as well. So this actually is a very high-level overview of the proxy architecture. So next, I want to actually give some additional details about how the extensions are being built. So the way the extensions, as you remember, as I mentioned before, the Baffle extensions are needed to perform advanced operations like sorting and other operations, or any database operations on encrypted data. So there is a model where we can do the whole architecture without extensions as well, with only the proxy. But in that case, without extensions, the only database operations that is supported is only equality searches. So with extensions, all the operations are supported. The way the extensions are implemented is like any typical other extensions such as PG vector or CA text and so on and so forth. So our Baffle extension basically has defined its own user-defined type, UDT, called Baffle counter 2. So this is the data type that actually stores all the encrypted data in the database layer. So the extension also includes the functions like encrypt and decrypt function for this particular data type, Baffle counter 2 data type. So this is, and in addition to the extension function, the extension also includes operator functions for this particular Baffle counter to data type, such as hashing, greater than, less than, equal to, etc. So these operator functions are needed for supporting indexing and constraints on the encrypted columns or encrypted values. So the extension is, it's very a typical extension. I mean, it has its own data type, it has its own set of functions, and then it has its own set of operator functions for supporting indexing and constraints. So this makes sure that we actually are able to support all database operations with these extensions, including indexing and constraints as well. And of course, I mean, the one thing I want to mention is the encryption can also be either deterministic or randomized, depending upon the needs. If it is randomized, even though the clear text data may be the same clear text data may have two different randomized values. It's more for security. In the deterministic encryption, the same clear text will have the same ciphertext. This basically is the extensions architecture. So now I want to actually go over, how the whole end-to-end flow works, right? So I'll go over I think this little bit dense. I'll go over the picture, which is actually makes more clear. The way the whole thing works is, as I mentioned before, all the connections from the application, database connections from the application goes through the proxy. The proxy ends the connection, and then actually we create one-on-one connection on the downstream to the database. So if it is SSL is being used, SSL is terminated in the proxies because proxy has to look at the queries and the data. Now, proxy actually, during connection establishment, one additional step the proxy does is what is called secure key injection. So for Baffle extensions to work on, to make sure that to support advanced operations such as wildcard searches or filtered queries or sorting and all the stuff, order by and stuff like that, they need the encryption keys. So as part of connection establishment, the proxy actually securely injects the keys to the extensions in the database. Now, actually, the proxy and extensions are in sync. Now, as I mentioned before, the SQL queries are transformed by the proxy, and then the transformed SQL query hits the database, and then the extensions in conjunction with the proxy make sure that it enables all the database operations. And similarly, as the encrypted result set comes back to the proxy decrypts the result set, applies the RBAC rules, masking and stuff like that, before sending the protected or the masked result set back to the application. Now, as you see in this architecture, only the connections that are going through the proxy to the Baffle to the Postgres database will get the keys, the encryption keys. So any lateral connections directly to the database, I mean, these are the connections the database administrator will typically do for managing the database. Those connections will not get the keys. So anybody, if the database is being managed by the database, by the third-party database or hosted databases or third-party database management services, then anybody actually, managing the database, connecting to the database laterally with direct connection to the database will not get the keys and hence won't see the clear data. They'll see only encrypted data. But they can continue to do whatever operations they were supposed to do, in terms of managing the database. But there is no risk of data being exposed to them because the keys are not available. Similarly, any hacker or threat vector that accesses the database directly, the database layer, will not see the clear data. They will see only encrypted data because those connections will not, those sessions don't go through the proxy, and there won't be keys available for the extensions to actually do the decryption. So data will be encrypted for anybody accessing the database directly. So this is actually the high-level architecture of how or the end-to-end flow of how the data is flows and how the key is actually used by proxy and Baffle extension in conjunction to make sure that none of the database operations will break. But at the same time, the data is protected by actually people that don't have a need for actually looking at the clear data. So this actually is an end-to-end data flow for the entire architecture. All right. So now I want to actually go over some of the transformations that are done by the proxy, and how what kind of SQL query transforms are done by the proxy. So as I mentioned before, I've given some examples. So in the case of create table query, in this example, the create table basically has one column marked for encryption, another column is left in the clear. So it's based upon the policy. So when this create table query is actually extracted and parsed by the proxy in the proxy layer, the proxy just transforms the data type of the encrypted column to Baffle counter 2. Because as I mentioned before, Baffle counter 2 is the user-defined data type, or the Baffle's own data type, extension data type, that is used for storing and processing the encrypted values. So this is basically how the create table, or even for create view, the same transformation is done by the proxy. Similarly, when an insert query goes through, the proxy basically parses the query and finds out the value belonging to the encrypted column, and then encrypts that value with whatever. If it is a multi-tenant use case, then that value is encrypted by the tenant's own key, so depending upon the policy, that value is encrypted. And then this transformed insert query, the insert query with the encrypted value, is then sent to the database for database to process. Now, obviously, the insert actually ends up with encrypted value in the database, so that value remains encrypted in the database layer. Similarly, for sort, same thing happens. In the case of sort order by, what happens is the proxy actually transforms the order by clause and embeds the Baffle decrypt data type UDF. This is a function, Baffle extension function, that decrypts the data and does the order by. So this actually function is embedded, UDF function is embedded by the proxy as this sorting while processing the sort clause or order by clause. The same thing for select list as well. When there is a select for an encrypted column, the proxy actually transforms that encrypted column and annotates the encrypted column with UDF. Baffle extension is UDF. And as part of the UDF call, it also needs a key ID. Here is just a key ID, not the real key. So the key ID basically is just a mapping of which key ID is used by which tenant in the case of multi-tenant use case. So that's the reason why there is a key ID here. But of course, the key ID is just the ID, not the actual key. So there is no risk of any key material or any clear data being logged in the database logs. The database logs will never have clear data, because as I mentioned before, the insert already has encrypted data, and also all these annotations, UDF annotations, will carry only key IDs. So the logs will not have any clear data or any of the keys. The same thing for filtered queries as well. In the case of where clause, there is annotation of the encrypted column with the Baffle extension UDF. The same for similar thing for group by as well. So, and similar stuff for distinct and same for aggregate functions also. If there's a sum or native functions, sum or average, any types of function, doesn't matter. The proxy actually transforms those queries with the functions, annotates the encrypted column with the UDF function, so that none of the native functions will break. All the functions will continue to operate even though the data is encrypted. Same with the wildcard search as well, like queries, right? The same thing happens. And with joins, similar stuff. But indexing, in the case of create index queries, there is no transformation. So as I mentioned before, the Baffle extension also includes operator functions for Baffle counter to data type. So whenever the B-tree actually indexing path is actually done by the database layer, for this particular data type Baffle counter to, the Baffle extension's operator functions will be called by the B-tree work algorithm in the database layer. So that is also covered. The indexing will be done on the encrypted data. Then the same thing with constraints as well. Whatever constraints logic that is already in the database, it will actually call the Baffle counter to operator whenever the constraints are actually enforced on this Baffle counter to data type. And the same thing actually is similar, and even for even not just for insert queries, the same thing is applicable for copy query in terms of bulk inserts, like typically done during the data analytics kind of pipeline where the bulk data is inserted, typically using copy query. So the way that the proxy actually, in the case of copy query, the proxy ends up getting a CSV file. The proxy actually, has in addition to SQL parser, it also has a solid CSV parser. So the proxy makes sure that the CSV file is transformed, and it is done in streaming mode for performance. And then that transformed or encrypted values in the CSV file is then sent to the database layer. So this is actually the brief overview of different query transforms by the proxy. So as I mentioned before, I mean, there is no limitations on any of the database operations. All the database operations will continue to work, even though the underlying column is completely encrypted using application layer encryption. So there is no need for the typically application layer encryption. Application need to extract the data out and do these operations. But in this architecture, there's no need for any of that stuff. I mean, the data, all the database operations can be used by the applications without any issues. So that's the query transformation part. Now I want to actually go over one more information about metadata query handling. So as we have seen before, the proxy actually modifies the data type of the original column to Baffle counter 2, right? So what happens is, because everything happens is transparently to the application, there is a need for not exposing this new data type to the application, because the application doesn't know about this data type. So typically, most of the applications do metadata queries and then finds out the column data types and all. So we make sure that the transform data type is never visible to the application. So whenever, so we actually enforce this thing by doing something called shadow information schema. This is something that proxy creates and manages within the database. So this one basically has the original data type of the columns that are marked for encryption. So whenever application issues an information schema query on that on a particular column which is encrypted, the proxy makes sure that that query is transformed to go to the shadow information schema instead, so that the application ends up getting the original data type, not the transformed data type. This makes the whole proxy architecture completely transparent to the application, even at the metadata level, so that the application doesn't have to, application always sees the original data type, even though the underlying data type is different, underlying data is actually encrypted. But this is the case where actually we use, where we actually transform the data type. There are cases where we actually use something called format preserving encryption, where we use the original data type itself. That is a different mode that is also supported in some cases. So this is how the metadata queries are handled. So now I actually want to go add one more. So we have also, so in addition to the native data types that Postgres supports, this whole architecture also supports data types by other extensions such as PG vector. So the PG vector basically is an extension for Postgres that actually makes the Postgres to behave. I mean, to make use of Postgres as a vector database. It kind of makes sense because this Postgres database already has data, and creating vectors for those data, it makes sense to have the vector in the same database instead of actually having another database, right? So that's the reason why PG vector has been built, and we actually also support encrypting the PG vector data types. So because the vector data types is also on confidential data needs to be secure, because there are ways to actually reverse the vector data to find out the original data. So there is a need for not only encrypting the data such as text or integer in the Postgres database, there is a need for encrypting the vector data types as well. So the proxy does very similar. I mean, it's no different from how it actually transforms the queries for other data types. Even for vector data type, the proxy transforms vector data type into text and then encrypts it and then stores it in the Baffle counter 2. And also the Baffle proxy along with extensions also support, even though the PG vector data type is encrypted, all the PG vector functions like L1, L2, cosine and inner product, Jacquard, and all those distance functions that are part of the PG vector continue to support, will be supported even though the vector data type is encrypted. An additional thing here is the PG vector also comes with its own indexing. for vector data types like IVF flat as well as HNSW. So in the case of those indexes, we do something called decrypted index. So in the case of those create index queries coming for the vector data type, we make sure that those those indexes are built on the clear vector. This primarily for performance reasons, to make sure that there is no performance hit because of vector encryption, vector data type encryption. And also, we don't want to change the PG vector source code. We want to make sure that everything is transparent. That's the reason all the functions are supported. The vector data type is encrypted. Indexing the PG vector indexes are also supported in the decrypted index format. So that is, this is very similar. I highlighted PG vector because that is the one that is actually getting a lot of added recently, and that is more relevant for the Gen AI purposes. But we also have the similar model for other data types such as CI text. CI text has its own extension. CI text is a data type, case insensitive text. So that is also supported in a very similar way. So that is actually on the support for PG vector. Now, basically, I want to actually go over the different how the extensions the Postgres extensions were implemented by us. So we actually started with building the extensions with C++. This was before PGTLE and PLDES came into picture. So we actually built C and C++ based extensions, and then that's where we deployed. That's what we have deployed with our customers, especially in on-prem environment. So obviously, C++ extensions are high performance, but low compatibility. The compatibility in the sense we cannot install the C++ extensions on hosted databases such as AWS RDS, etc. So we cannot store, obviously, because there we have to go through. It's not actually possible to install C++ without going through the hosted database providers, security reviews and stuff like that, which is actually which is kind of hard to upgrade, and it's a long drawn process. So that's the reason why it is low compatibility. It cannot actually work on. It can work on on-prem database or self-hosted Postgres databases, but it's not compatible with the hosted databases. Now, in the case of database as a service or hosted databases, we have two other options. So we ported all the extensions that we did in C++ into PLPG-SQL. And that's the first thing that we did. This is before PGTLE came into picture. So this is PLPG-SQL based extensions have low performance because, as you know, PLPG-SQL is lower in performance. It's not as cannot be as performant as C++, but it's high compatibility. It doesn't matter whether the database is hosted or self-hosted or third-party hosted or database as a service. PLPG-SQL based extensions can be installed, and then can be used for the transparent application layer encryption. But most recently we added, we actually ported all the extensions to one more language, which is Rust language. So because there is a lot of this good support for PGTLE and PLDES open source initiatives, which enables actually the safe installation, building extensions in safe languages and then installing them in the database and then using it. So now we are ported to the Rust language, and then we are utilizing PGTLE and PLDES extensions to install our own Rust extensions in the Postgres database and then using it. So this is the most performant or high performance. The Rust-based extensions that we have built is very similar in terms of performance when compared to C++. And of course, it's high compatibility. Obviously, the database hosted database providers such as AWS RDS support PGTLE and PLDES. So we are able to install these extensions on those environments. Customers using those database as a service environment, we can enable those customers with transparent layer encryption without going through the process of enabling C++ with DBaaS services. So the PLDES is actually our most recent and most deployed version, and it actually performance-wise it's high performance, and it's actually high compatible as well. So this is basically the different approaches that we took in building our extensions and based upon the availability of the PGTLE and PLDES. So I just want to quickly go over some of the challenges that we faced for PLDES. Some of the, a lot of them are addressed already by PGTLE and the PLDES community. So there were some issues with enabling we basically have to passing the user-defined type as a parameter to the REST functions. We have to actually build a PLP SQL wrapper, and then which in turn calls the REST function. So that's one of the workaround that we have to do. And there's some other support for data types such as bit, money, CATX were not supported. I think those are all the supported in the recent versions. So we are covered over there. So yeah, that's our journey and building these extensions with different languages and enabling this transparent application layer encryption. So now I'll go over the summary and then open up for questions. So of course, as I mentioned in the previous slides, the application layer encryption is what is needed to address the current threat vectors. The existing transparent data encryption is no longer, it's not relevant for the current threat vectors. So there's a need for application layer encryption. But application layer encryption or client-side encryption basically has its own challenges. I mean, obviously, it will break the existing. It needs code changes to the applications, so it won't work for the legacy or off-the-shelf applications, and it actually breaks the database operations, and then it also puts a burden of key management with the database with the application developers. So the proxy-based solutions make sure that all these three challenges are covered to enable transparent application layer encryption seamlessly without needing to change the application, and then making sure that all the database operations are supported. So with the use of proxy-based approach and the extensions-based approach, we're able to accomplish that. So yeah, that's pretty much the slides that I have. So I just want to open up for any questions if there's any.
Okay, it looks like we've got a couple of questions in chat. Someone has asked, are there any impacts on performance on the database side since the data is encrypted? Okay,
that's a very good question. So obviously there's more work is being done by the proxy as well as the extensions because there's an encryption decryption happening. But we have actually added a lot of optimizations. First of all, we are using the standard AES encryption. So the AES encryption is pretty much hardware offloaded. The CPUs basically have hardware instructions for doing those for supporting those algorithms. So as we are using the standard AES encryption, that overhead is gone away. So that is fully hardware offloaded, and this offloading is available in all the CPUs. In all the Intel, AMD, it's widely available. It has been around for many years, and this is what is used by SSL and other encryption solutions as well. So that is one major advantage of reducing the performance. And also we have a lot of other performance optimizations within the proxy level and within the extension level as well. And of course, as I mentioned, Rust is a high-performance language that actually take care of additional performance overhead. And also the proxy has a lot of filtering. I mean, the proxy does not parse all the queries. It parses only the queries that basically has tables that are marked for encryption. So just multiple layers of filtering and stuff that happens. A lot of bypassing happens if the table is not encrypted. So we have actually make sure that the overhead of encryption decryption is not perceptible by the user. We heavily run the TPCC benchmark with all the columns of TPCC benchmark encrypted with a group of columns encrypted and so on and so forth. So even if you encrypt 60% of the columns in TPCC benchmark, our overhead is in single digits only. So that's basically the performance part is well covered by the implementation and all the optimizations that we have done over the course of the years.
Great. And we have one more question. Would the Netty network stack work with the ADBC or Flight SQL as well?
Yeah, so basically the whole thing is in the network layer. So as long as because the proxy understands the client-server protocol, so it doesn't matter what kind of language or what kind of driver is being used in the application layer. So it's transparently supported.
Great. Do we have any more questions? Doesn't look like it. All right, just a little more business before we wrap up. Thank you so much, Rajan. Great talk. Thank you, PGUS and PGX, for sponsoring. Our next SF Pug is Tuesday, November 12th with Be Thankful, Logical Replication Traps You Did Not Fall Into and How to Get Out of Them with Casey Holston. Tuesday, December 10th, we have a first look at PostgreSQL 17 with Christoph Pettis. Tuesday, January 14th, we have BM25 full text search in Postgres via Tantivy with Philippe Noel. Upcoming conferences are PGConf EU, October 22nd through 25th in Athens, Greece. All Things Open, October 27th through 29th in Raleigh, North Carolina. PG Day Med, December 5th in Naples, Italy, and their CFP is still open through the 13th of this month if anyone wants to put in papers for that. We will send a link by email when the video is ready, and you can watch our social media. You can find us on Twitter, LinkedIn, Mastodon, and Blue Sky by searching for Bay Area Postgres. We are looking for speakers for 2025. If someone you know or you are interested, please contact us. Thank you so much for attending, and have a great afternoon. Thanks so much.
Thanks.
Bye-bye.
Thanks, everyone. Bye.